welcome to this video that continues our discussion of the definite integral. This is part of lecture note 6.1 for Math 1431, Calc 1 at the University of Houston for the spring of 2020. So in the first part of our notes, last time, we discussed this actual area under a curvy function. And a good name for this is the definite integral. What I should actually point out, first off, is that this actual area, it's really a signed area. Right? This quote-unquote area can be negative or positive. The examples we saw last time focused only on examples or functions where this number was approximated by positive numbers. But if I give you a function that looks like this, then this actual area under this function, this curvy area, some of it's negative. Let me actually shade that a different color. Some of this area is negative. Maybe I'll shade that in orange. So this orange area here is negative because it goes below the x-axis. Right, and so if we had set up rectangles to approximate that orange area, those rectangles would have negative heights, and that's where the negative area would come from. Okay, but what else did we discuss last time? We said that the way we were going to think about approximating this actual signed area, we were going to approximate it by using rectangles. And our rectangle area would just be width times height plus width times height plus width times height, and all the way up to width times height. And we practiced initially 3 different ways of producing these widths and heights. The first 3 ways involved left endpoints, right endpoints, and midpoints. What was interesting about these first 3 ways is for all of these ways, the widths were always the same. Our rectangles always had the same width, no matter how many rectangles we were using. So whenever we saw the instructions use left, right, or midpoints, we knew that we had a common width where delta x was just b minus a over n. The only thing that was changing for each of these was what we would call the height of each rectangle. If we're using left endpoints, then each height of our rectangle would be obtained by plugging in the left point of each piece. If we were told to use right endpoints, then each height would be obtained by plugging in the right point of each chopped subinterval. And then, of course, if we were told to use midpoints, the heights would be obtained by plugging in the midpoint of each chopped subinterval. So we practiced a couple examples using these instructions. Usually we were told to use a small number of rectangles, like 3 or 4. And then we ended last time by discussing 2 other ways to use rectangles to approximate this curvy area. And these were called upper sums and lower sums. And so the upper sums, the notation for that was a capital U, and the lower sums, the notation for that was a capital L. One thing that was different about both of these things was that the widths now were not given by a fixed number. It wasn't given by delta x. The widths were given by saying, here, just chop up the interval into these pieces, this partition P. And that happened with both of these. So the partition, the way we chopped up or created rectangle widths, some of the rectangles could be wider, some could be thinner. And then the actual y values that we were using, the heights for upper sums were given by looking at the maximum y value over each piece in the partition. And the heights for the lower sum were given by looking at the minimum y value over each piece in the partition. So our upper sums, because we were looking at biggest y values, this gives us an overestimate of signed area, and our lower sums, this is going to give us a lower estimate. And so I can say, oh, what we're really saying, right, is that the actual signed area, this term here in the middle, is of course trapped above by using tall upper rectangles, no matter what partition you're using, and it's bounded below by using short lower estimate rectangles. So the real big idea here is if the number of rectangles, we usually call that n, goes to infinity, then maybe our lower sums turn into some number. But as that happens, maybe we're always setting up upper sums, and that turns into the same number. What this tells us, when this happens, is that, hey, if we use more and more rectangles and create overestimates and underestimates, those overestimates and underestimates become the same number. What that tells us is, oh, we've just found the actual area. And this is actually how Riemann defined what we now call the definite or Riemann integral of a function. It's trapping the function below by certain rectangle areas and trapping its area above by other rectangle areas and taking a limit of those two rectangle areas and seeing if you get the same number. So I just want to point out one thing, that computing what we call definite integrals is tedious. And our previous examples from part 1 really speak to this. So this is maybe note 1. Right? How do we actually compute one single estimate? Well, we say pick a partition, or pick an evenly spaced width, pick delta x, pick a number of rectangles. Last time I think one of the examples we did was the area under 1/2 x squared, and we used 3 rectangles. So when we used 3 rectangles, we had to carefully set up what are the 3 widths, what are the 3 heights, and then we added up those areas. What this is saying is, to get the actual definite integral, the actual area, don't just do n equals 3. Do n equals 3, do all the steps, get a number. Now do n equals 4. Repeat the whole process now with 4 rectangles. Do all the steps, get a new number. Now repeat the process for n equals 5. Do all the steps, get a new number. You keep doing this for n equals 6, then n equals 7, and then you hope to spot a pattern so that as n goes to infinity, you can see what these areas start to actually become. That is really, really tedious. But thankfully, coming up in the next section, the fundamental theorem of calculus gives us a way to not do it in this tedious manner. So the fundamental theorem of calculus is a rescue tool that says, hey, these annoying to compute actual signed area definite integral things, here's a faster way to compute them. Because I've made that comment, I also want to comment that in real life, it turns out integrating is actually useful in real life. I kid you not. In real life, especially if you want to go on to do stuff involving any sort of STEM field, integrating is a basic tool that actually helps you in a lot of problems. You want to be able to add up, compute the definite integral of a function to get some information. And in real life, when you do this, most of the time, the fundamental theorem of calculus is useless. It doesn't apply to your real life situation. And so you have to compute these things by approximating the definite integral, maybe using rectangle area, like we've been studying, or maybe using some other sort of straight area, maybe trapezoid area, something like that. But this is still an active field. How do we come up with better ways, maybe ones that are faster or more accurate, to approximate curvy area? This is an active area called numerical analysis, and it's kind of a big deal. Okay, so those were sort of my two comments. What's going to happen in the rest of the notes here in this discussion is we're going to focus on the actual area, and we're not going to focus so much on how tedious it is to compute. We're just going to say, well, suppose we could compute it, or somebody told us what it is. What are some ways to think about this actual area, this definite integral? What are some properties it has? That's what the rest of these notes are about. Okay, so as we've discussed, the number representing this actual area is called the definite integral. And I just want to sort of go over how we talk about this in a calculus class, literally how some of this stuff is pronounced. So when you see this mixture of symbols, it is correct for you to think of the term actual, and I'll say signed area. This is really, really smart to have this always in the back of your mind. But the way we're going to actually pronounce this when we see it, right, this is what this thing is computing. The words we end up using in a math course is we say this is the integral from a to b of the function f of x, and then with respect to x. And that with respect to x, that's what this dx is telling us to say. Oops, sorry, got the wrong color. So each sort of symbol in this conglomeration has a meaning and has a way of saying it. This capital S thing is called an integral sign, right? And it really is made to look like the letter S, maybe stretched out, because it's supposed to remind us that, hey, this is a limit of sums of areas. The number a, which starts our interval, is called the lower limit of integration. The number b is called the upper limit of integration. The function whose curvy area we're trying to compute under is called the integrand. And lastly, this dx guy tells us the independent variable is x, and it also reminds us that we were talking about widths of rectangles that were getting thinner and thinner. So in other words, what we really had before was like a summation sign like this, and what we were adding was information about heights, I'll say maybe widths, w's, times heights, right? And what we said was, well, especially if we're doing a partition where all of the widths are the same, where all the widths are the same, we just gave that the name delta x for a little bit of x width. And then each height, right, was usually given by plugging in an x value into our function f. And so if I just rewrite the order of those two, right now I wrote it as widths times heights, but if I write it as heights times widths, right, what I have is I have a y value for some height times some particular change in x values for widths. And usually we would maybe stop this sum at by stopping the number of rectangles in. But if we say, well, let's keep making the number of rectangles go up and up to infinity, then our clunky finite sum of rectangle 1 plus rectangle 2 turns into a smoothed out continuous sum, so there's our integral sign, of the values of f of x, those are our heights, times these now shrinking widths, right? These widths were getting smaller and smaller, so we call them dx to acknowledge that they are getting really, really tiny. And the only thing I want to acknowledge now is tell you where my interval started and stopped. So what I've actually sort of written up here and attempted to color code is actually something that happens in a lot of math and applied math courses. You will have a finite process, like a finite sum. And if you want to turn it into, take a limit of these things and turn it into an infinite or continuous process, your finite sum will turn into an integral sign. Your finite width will turn into a symbol that acknowledges, hey, this is a limit of widths that we're getting really, really small. Okay, so as mentioned at the start of this part, it turns out that when we do this process, when we compute and integrate up all this stuff, the integral can be 0, negative, or positive. And that's just because our heights, if we want to think about this as coming from rectangles, were y values. And these can be 0, they can be negative, or they can be positive, right? They're just y values. And this process of trying to calculate these definite integrals, we just call this integration. And again, I do want to repeat this warning right now, or this reminder, it's not really a warning, that right now you want to think of this term integration as a tedious, difficult process. This is a tedious but important limit of signed rectangle area. But if you go talk to any of your math friends who have gone through Calc 1, they will say integration. No, it's not that. This equals anti-differentiation. So right now, at this point in our calculus careers, there's a bit of a disagreement. But it turns out this point of view happens after we get the fundamental theorem of calculus. Okay, so again, let's focus for the rest of this part of these notes. Let's focus on properties of this definite integral, setting aside how difficult this definite integral might be to compute. So the first property should be an obvious one. It says, property 1, that the definite integral of a function, f of x, from a to a has to be the number 0. And let's think why this is true. And the reason this is true is because we can think of these definite integrals as signed areas. So I'll draw a little picture to show what's going on. I don't care what your function looks like, f of x. It can be a really weird function. It can even have some discontinuities and stuff. I'm going to draw it as though it's pretty nice. So maybe this is f of x, something like that. And if I say, hey, tell me the integral starting at x equals a, and not ending at x equals b over there, but ending at x equals a again, how much area is under this function over that one point? How much area is in that little red line segment? Well, it's just a line segment. It has 0 area. And that's why the integral of f of x from a point to that same point is always going to be 0. Okay, property 2 says, hey, what happens if your limits of integration get flipped? And if you really think about what our limits of integration were referring to, that would tell us to chop up an interval, right? We assumed, as this little typed note to the right makes mention of, that the number b was always bigger than, right? And then what did we do with this? Well, we would chop this up maybe into a partition, maybe an equally spaced partition with delta x's. So if I had delta x, I would have said, well, my widths are b minus a divided by the number of rectangles I'm using. But if you flip b and a, right, then what's going to happen is these widths are going to be negative if you flip b and a. And so you're going to get a bunch of rectangles with negative widths, and so you're going to get a giant minus sign popping out in front. Okay, so property 3 here is one that really isn't too surprising. It says, hey, how do I think about the definite integral of a sum or difference of two integrands, of two functions? And it's exactly what you would want to do. You just take the definite integral of each separate function and sum or difference their area. Property 4 is also not that surprising. How do I think about the definite integral of a function, but now I've multiplied every y value in the function by k? Well, if you think about what that's doing, if your function originally looks, say, like this curve, maybe that's f of x. When you multiply by k, especially if, say, k is some positive number, say bigger than 1, then this point here gets multiplied up. It gets stretched up there. All these points maybe get stretched up by some factor, right? And so this might be k times f of x. So what are you doing whenever you set up a rectangle area here? You may not have changed the width, but you sure have changed its height. You now have a stretched rectangle. You've stretched each rectangle in your approximation, stretching the height by k, and so that makes the total area k times as big. So that's what this property 4 is saying. You can take out this k and just put it out front. It's k times the area. Okay, so this is a really good type of example. They've actually done all the tedious work in example 4. Example 4 says, suppose we are told that the definite integral of some function from 1 to 5 is the number 10. I'm going to stop there. This right here, how did they get this? They presumably took a limit of rectangle area, and they said, okay, don't worry about that. We're going to hide all that work from you. Just use the fact that this actual signed area is 10. And similarly, they tell us from 1 to 5 for g of x that its signed area is 4. And they tell us all this information. So what they've told us in this problem is a bunch of tedious to compute information, and we just want to use that information to see if we can answer the following questions. So this question won't involve us setting up rectangles and delta x's and n's and heights. We're just going to use each of this green stuff as information about signed area. Okay, so let's see if we can use this signed area information to figure out part A. It says, given all this information, what must be the integral of f of x from 10 to 10? And actually, they didn't need to tell us any of that information. This has to be 0. That's by property 1. That's because there's no signed area over a point. Now, let's think about property 2. Question B. It says, all right, if we tell you all that green information that Casey boxed, how do we figure out this definite integral? And this is where you can use some different properties. You can first say, well, wait a minute. I'm now integrating, adding up f of x minus 2g of x. I can break that up into two definite integrals. Pull the minus sign out front. And I can break this second definite integral up even more I can pull that 2 out front. Right, so this is me just practicing those properties I mentioned. I'm pulling that constant out front, and now look, this guy here, they told me this number. They told me that area. They said from 1 to 5, that's right up here, you're supposed to get 10. And then they said, this area, they also told me, they said when you go from 1 to 5 for g of x, you're supposed to get 4. So this becomes 2 times 4. So at the end of the day, this was just asking you, hey, what's 10 minus 8? All right, let me zoom out here so I don't have to keep scrolling up and down. Let's see if that's enough. That might be enough. Okay, so for part C, now they said, hey, what's the definite integral from 5 to 6 of f of x? Well, if I go look at that green boxed information, they never told me from 5 to 6, right? But they did tell me these last 2 pieces of information. From 5 to 10, I get 6 units of area, and from 6 to 10, I get 8 units of area. So you don't have to think about a picture, but I like to first at least. What they told me here was from 5 to 10, I've got some function. I don't know what it looks like, but maybe it looks like this, right? Actually, so from 5 to 10, maybe I'll make it a little negative down below. So from 5 to 10, I've got some function that maybe, I don't know, looks like this. And the area, they told me the definite integral there. The area, that green area, they told me that's from 5 to 10. If I add up all that positive and negative green area, I get 8. But then they told me from 6 to 10, sorry, I said that wrong. They told me from 5 to 10, if I add up all that positive and negative area, I'll get 6. But then they told me from 6 to 10, if you add up the area, you'll get 8. So maybe in my picture, maybe this is where 6 is. So how do I figure out the area, the signed area, from 6 to 5? Well, what I really want, right, according to my picture, I want this little bit of negative area. I want that little piece. How do I figure that out? Well, that's just the total area, 6, minus this area from 6 to 10. Right, so this guy, the property that I'm really using here, is that this equals the integral from 5 to 10 f of x dx minus the integral from 6 to 10 f of x dx. And so what I get here is, well, this was the number 6, this was the number 8, so this little blip of area I had to be negative 2 signed units of area. So let's try part D. It says, what is the integral from 5 to 1 of g of x? Well, if I think about this guy, if you don't like seeing the lower limit of integration being a number that's bigger than the upper one, you can always flip them at the cost of introducing a negative sign. So, and hopefully they told me enough information to do this definite integral up above, and I think they did. So this should be negative, and I'll go and look it up in the box information above. The integral from 1 to 5 of g of x was 4, so this should be negative 4. Okay, so what's going on at this part of these typed notes is they're discussing what we've already talked a little bit about, both in our previous section and at the beginning of these notes, which is that areas, right? Whenever I talk about the word area, I tend to think of this as non-negative. So if I have a function like here in the second example that sometimes dips below the axis, right? I can talk about the integral from a to c of f of x dx as computing a signed area. That scratching you hear in the background is my little dog making a nest for himself, in case you hear it. Anyways, okay, so the signed area, if you really think about this, this will be the area of the first region, that positive number, minus the actual positive area of the second region. Right, this is sort of what these type notes are getting after. By the way, those symbols are capital Greek letters. Those are omegas. And so we're really saying that, hey, we've got this trapped region we could call omega 1. It's trapped above by the curve f of x, but omega 2 is trapped, it's a region below the x-axis, trapped underneath by the curve f of x. Both of these regions have positive areas, but if I subtract the positive area that's below the x-axis, that'll represent this total signed area given by this definite integral. Okay, so let's try example 5. I think this is clearer than reading through the type stuff. So for example 5, what we have is the following. If we're told this is a graph of f of x, and if we're told the area of omega 1 is 12, and the area of omega 2 is 8, then what is the total definite integral of this function from a to c? Well, the previous theorem and our properties from before lets us break up this integral into two integrals. What I'm really saying is, oh, I could compute the area relevant to that piece from a to b, that's this, and then compute the signed area relevant to this piece from b to c, that's this. And oh my gosh, they already told me what these two numbers are. They said the area under f of x from a to b, that's the area of omega 1, that's 12. And the area of omega 2 is 8. And the only mistake you don't want to make now is saying I'm going to add these. You're not going to add these because the omega 2 region, it does have area 8, but when we interpret it as a definite integral, we would need to interpret this as having negative signed area. So it's true to say that the area of omega 2 is 8, but when we write this as computing the area, the signed area, under f of x, that's a negative 8 because it's below the x-axis. So this should be 4. So this is the type of question that we like to ask our students. That's actually a lot better to ask than one that requires you to set up a whole bunch of rectangle information, right? Because the whole bunch of rectangle information, it's really easy to make a mistake there and throw everything off. This sort of question in example 5 really highlights, do you understand what this integral symbol is telling you? Do you understand what it means and how to manipulate it? So let's try example 6. Example 6 gives us some information. It says, here's a graph of a function y equals f of x. And I'm going to focus on the instructions first. It says, find the area between the curve and the x-axis from -1 to 5. So from -1 all the way up to 5. So I'm going to sort of highlight different parts of this area they're talking about. Maybe this one's in green, maybe I'll keep this one in green, and then maybe I'll switch and do this one in a kind of red. So when this problem says find the area between the curve and the x-axis, we should really think of this as, as three regions. And you could call one of them, if you want to use like the previous notation, we could say, well, one region is like an omega 1, and then we'd have an omega 2, and then finally we'd have a third region, omega 3. And so what we really want, we got to pay attention here. Go back to the question and say, what were they asking me to find? Did they say to compute area or signed area? And here's an important thing. The word area all by itself, I'll remind you of this, is always positive. So if a question asks you for area, your answer has to be a not negative number. But the word signed area, and another word for this now, right, is definite integral. This can be negative, this can be 0, this can be positive. So for this question, these three regions that I've highlighted and named are clearly relevant to what we want to do, but we want to pay really careful attention. Did they tell us to find the area or signed area? And if I go and read the instructions, they want the area. So we're not just going to set up a definite integral, because a definite integral could record some positive and but also some negative area. So we want to be careful here. Because they use the word area, we want everything involved to be positive. So now let's go and look at this information they gave me. They first told us in the start of the problem that the definite integral from -1 to 1 of f of x is 5. What that's telling me is this little green area here, this is 5 units of area. And then they told us that the definite integral from 1 to 4 is -12. So that tells me the signed area here is -12. Right, there's where my negative rectangle heights would come in. And then lastly, this area from 4 to 5 is 4. So that's a positive area. That's for this third region, 4. So because they asked for the total area, not the signed area, we're going to say, oh, this guy has area 4. This first guy had area 5. And that red guy, he has signed area -12. But so he just has regular old area 12. And so the total area, right, I'm just going to add all these up to get the total area, will just be 5 plus 12 plus 4, which is just 21. Okay, so maybe I should pause here and do a quick couple popper questions. So popper question 1. Let's do a question like this. Let's say I have a really terrible function. It's just a weird looking guy, and his graph looks like this. I guess I gotta extend my axes a little bit. And let's say that's x equals 0, and that's maybe x equals 1, 2, excuse me, 3, 4, 5. And so here's my question for popper 1. It's about this function, y equals f of x. My question here is, which number is biggest. So I'm going to give you three numbers. Sorry, I'm going to give you several numbers, maybe 4 or 5, and I just want you to record the biggest one. Okay, so option A will be the integral, the definite integral from 0 to 2 of f of x dx plus the definite integral from 4 to 5 of f of x dx. Option B will be a shorter looking expression, the definite integral from 0 all the way up to 5 of f of x dx. Option C will be the integral from 0 to 4 of f of x dx. And option D will be the integral from 2 to 5 of f of x dx. So I claim, even though I haven't told you anything about the outputs of f in terms of numerical values, I haven't said exactly what this scale on the y-axis is, I claim that there's enough information in my picture for you to make a meaningful choice here. And what you want to think about, I'll sort of shade this picture maybe like we did in the last one, is these definite integrals represent some signed areas, right, trapped under my function and between the x-axis, and some of the areas might be negative. So some of the answers might involve adding a negative number, while some of the answers might involve adding up only positive numbers, right? So for example, okay, so I hope this makes sense for how to think about which of these numbers should be the biggest number. What you're really looking for is these 4 integral expressions represent different signed areas. Which of these signed areas has to be bigger than the others? All right, so let's try a second question. Popper question 2. Is it possible for a non-constant function, so not a flat line function, to satisfy this following property? Is it possible to do this? Say from, I don't know, from some number a to some other number b, when you compute its definite integral, you compute up its signed area. Is it possible that this equals 0? And I'll even say, and don't cheat, don't make a equal to b. We'll make them 2 different numbers, right? Is the answer A, yes, this is possible. It's possible for all your signed area to cancel out. Or B, no, this isn't possible. And if you want to think about some pictures that might be helpful, here's one that you could really think about that you really know, like maybe something like y equals the sine of x. Right? So if I try to sketch a picture of this guy's graph, from like negative pi to pi, and of course the graph goes on, right? But at least from negative pi to pi, this is what the graph really looks like. And if I were to look at the signed area in these situations, maybe I'll do this one. I'll try and color code it the same way. I've got some signed area under this hump, and I've got maybe a different valued signed area under this hump. What maybe happens with those 2 signed areas when you combine them? Okay, so there's not too much longer to go in this section. There's some other really nice properties that make this definite integral easy to think about, even if, again, it's very tedious to actually compute this as a limit of rectangles. So the first property, maybe I'll zoom in again. The first property here, they call property 1 for other properties, is the definite integral of a constant is just the constant times the length of the interval. And let's think about why this is true. It's really simple. If I have f of x as a flat constant, maybe it's a positive constant. So there's y equals the positive number k. And if I'm integrating from a to b, well then what am I doing? I am looking at all of this signed area right here. And oh my god, if you really think about what that is just a rectangle. And what's the height of that rectangle? The height of that rectangle is, of course, the y value k. And what's the width of that rectangle? Well, it's the x length, and that's just the size of that single interval. That's just b minus a. Right? And by the way, my picture here also works even if k is a negative flat number. Right? If k is that orange line, but it's presented down below, then this is still going to work. It'll just be a negative height. So it'll be a rectangle with height negative k, or k, whatever negative number it is, times that width, b minus a. These other properties that follow, properties 2 and 3 in particular, are telling us something that's really not too hard when you think about definite integrals as areas or signed areas. When I think about, for example, in property 2, if you tell me I've got two functions and the function f is always taller than, it always has a y value above the function g's y value, then the area under these functions also compare in the same way. That is, the area of f of x is bigger than the area of g of x. And you can really think about this. Again, I'm going to do this in terms of thinking about maybe both of these functions being positive, but it really doesn't matter if some are negative. If my curve f of x is always above g of x, maybe that's f of x, and then g of x is this other curve, I'll make it dotted, it's always less than, then it's pretty clear to see that the area under f of x, I'll shade as green, is going to be more. It's going to have more positive area than the area under g of x, which I'll try to shade in blue, but you can't really see it. Right? The f of x area is above the g of x area. So that's all property 2 is saying. Property 3 can also be understood visually. What it's saying is, if you have a function, right, f of x, and if it's always trapped below a constant value, say capital M, and if it's always trapped above a constant value, say little m, right? So f of x is some function, and it's always above or below these two, right? So maybe it starts off here, maybe it goes like this, right? So that's f. Then the area underneath f, and we really mean the signed area underneath f, so some of it might be positive, some of it might be negative. The signed area under f, well, clearly it's less than this biggest area under the capital M, right? Because that's all of this, under capital M, it's less than this, and it's bigger than this negative area, right, between little m and the x-axis. Okay, property 4 is really what my first Popper question was sort of had to deal with. Yeah? Property 4 really dealt with, okay, what if you have a definite integral of a function, and if your function's positive, property 4 is not really saying anything, but if your function is occasionally negative, then there's f. And so let me shade this area according to where it's positive and negative. I might have some positive area under f, and I might have some negative area under f. And so if I first compute all that area, right, and then take the absolute value of that, that's where question 4 is starting, property 4 is starting. That's going to be the green numbers minus the red value. And I say, well, how big is that, whether it's positive or negative? That's clearly going to be less than adding up the positive version of f. So that second positive version of f, the absolute value of f, says, okay, well, here's f. It's positive. Absolute value of f is f. Oh, now f is negative. So its absolute value will switch to being positive. And then f is positive again. So the second graph I've drawn has nothing but positive area underneath it. And so it clearly has more area than the total area of the original function. Property 5 is all about our second Popper question. Right? If f of x is an odd function, and I'll remind you that odd means f of negative x equals negative of f of x, then when you integrate from a negative a to a, right, you have just as many negative inputs as you do positive inputs. And so you'll have, by the odd property, just as many negative heights as you do positive heights. All the signed area has to cancel. Right, and I have a nice little picture here. Here is a picture of a type of odd function. It's odd because the y value here is negative of the negative x value. And when you do this, what you end up with is a bunch of negative signed area that will cancel out perfectly all of this positive signed area. Similarly, they mention, hey, if f is an even function and you're integrating from a negative number to its positive version, that's just twice the area from 0 to that positive number. So if I look at this picture down below, right, the area of the blue region, this total area is 2 times the area of one of the blue regions. All right. So this is a good one that they're asking us to try, but I'll try and put it in here. It says, try this one. Find the lower sum. Now we're back to computing lower sums. All right, so this is from part 1 of our notes. For the function x squared, where x gets to go from negative 1 to 1. So this is, I'll just set this up for you guys to maybe finish yourself. But this mentions lower sums. And so that says, okay, we may have a partition that is equally spaced or not. And this partition we're given is not equally spaced. So we have a point negative 1, first point in our little breaking up. And then we go to negative 3/4, which would be about here. And then we jump all the way to positive 1/4, which would be about here, I think. And then we go to 1/2, and then we go to 1. So let's count. There were 1, 2, 3, 4, 5 points in my partition, and this is going to give me 1, 2, 3, 4 rectangles to set up. Right, so we see we're going to have 4 rectangles, and our partition tells us the width of each rectangle. The first rectangle has width equal to negative 3/4 minus negative 1, so that'll be 1/4. The rectangle next to it, the little piece next to it, is going to have width W2 equal to 1/4 minus negative 3/4. That'll be width 1. And then the green rectangle that's going to be next to that one will have width W3 equal to 1/2 minus 1/4. That's 1/4. And then my last blue rectangle for my color coding is going to have width 1 minus 1/2. That'll be 1/2. And now they told us to use lower sums. So to create the heights of these rectangles, I've got to look at each piece and plug in the point that's going to give me the lowest y value on that piece. So back to my orange interval from -1 to -3/4, I say, okay, what's going to give me the lowest y value? Well, I clearly see that's going to be here at -3/4. So my first height is going to be whatever number I get by plugging in -3/4. And that's going to give me this rectangle here that I can try to shade in orange. Okay, my next rectangle for this little try this question. What's the smallest I can make the height on the interval between -3/4 to 1/4? The smallest I can make the height, I can actually make it all the way down to 0. So the height here is going to be a lovely number. It's going to be f of 0, which is just the height value 0. For my green interval, I guess I use a slightly different green. My third height, again, I'm trying to make these as small as possible because these are lower sums. My third height is going to occur right here at x equals 1/4, and I'm going to get this little green interval, or sorry, this green rectangle. So my third height is going to be the f value at 1/4. And then finally, my blue fourth height is going to be, you can check, it's going to be the lowest y value is going to happen when I plug in 1/2 on that blue interval. That's going to be here. So here are my 4 rectangles that I am going to use according to the instructions for this problem. And so what am I going to get? I'm going to get that this rectangle area will be the orange area, which will be width 1 times height 1. So that'll be 1/4 times f of -3/4. And my function f just squares everything. So f of -3/4 will be 9/16. The next one I really like, that's just going to be the width 1 times the output 0 for the red height, plus my next width was also 1/4, and my height there was f of 1/4, so that'll be 1/16, because I'm squaring that. F of 1/4 is 1/4 squared. And then my last one has a width of 1/2 times f of 1/2, so that'll be 1/2 squared. So I'm going to stop this here. That'll be my answer, whatever number that it happens to be. That'll be something interesting. This next try one, I will let you try yourself. I'll leave this one blank. But let's try this last one, since it practices properties of the definite integral, not rectangle approximations. This one says, suppose we have the integral from 0 to 1 of f is 3, from 0 to 3 is 5, from 3 to 6 is 9, and from 6 to 1 is the one we want to find. What is from 6 to 1? So let's just try writing this out. If I say, hey, add up the area under f of x starting at 6 and going to 1, well, that's going to make all my widths negative. I can flip those around and go from 1 to 6. But I have to put that negative sign in there. That's one property that we used. And now I can say, okay, I want to start at 1 and I want to end at 6. Well, one bit of information that they did give us is that the integral from 0 to 1 of f of x dx was 3, and they told us the integral from from 3 to 6 of f of x dx, I'll write that one down next, was 9. And the other one that I was going to write down next was the integral from 0 to 3 of f of x dx was 5. So somehow I want to use all this information to see if I can get the integral from 1 to 6 to appear. Yeah. You can combine these two. If I add these two, right, the first one, 0 to 3, and then I pick up from 3 to 6. So altogether, this is integrating from 0 to 6. And so I learned that this is 5 plus 9. This is 14. But I don't want to go all the way starting at 0, right? I would much rather, or I've been told, that I want to start at, I want to start at 1. So maybe I'll switch colors here. So to go from 1 to 6, f of x dx, if you think about this, you could say, well, let me go all the way from 0 to 6. I know what that number is, but let me take away going from 0 to 1. I think this is the crucial step for understanding this exercise, the one I've just sort of cornered off there. That to integrate a function from, say, 1 to 6, I could go even longer, go from 0 to 6, and take away 0 to 1. So from 0 to 6, we just found is 14. From 0 to 1, we were told is 3. So this is 14 minus 3. This is 11. So the integral from 1 to 6 is 11. So finally, the integral maybe we're after is negative 11. All right, so let me just go here. I got to scroll around. Sorry to do that to everybody. We had 2 Popper questions, so let me do at least one more. So Popper question 3. Excuse me. All right. So given this picture, now I've got to sketch a little picture for you. Given the picture of a function f of x that I'm going to show you here. All right. And maybe I'll even tell you that this starts at negative 1 and it goes to 4. So this is y equals f of x. Oh, and I'll even tell you this height value, this maximum height value here is m equals 6. So given this picture, which of the following are true? And really, there's only going to be one statement I'm going to make that's true. So maybe statement A will be something like the definite integral from negative 1 to 4 of f of x dx, when I add up all that signed area, I get a negative number. Maybe statement B is going to say, when I add up all that information about f of x, that signed area, that's not only, it's not negative, it's not only positive, but it's bigger than or equal to 30. And then statement C might be the signed area from negative 1 to 4 of f of x dx has to be less than or equal to 30. And then maybe statement D would be that this definite integral from negative 1 to 4 of f of x dx is less than or equal to 18. So it's kind of surprising, right? I just drew this little picture with very little information, right? there's a little bit of information. There's that y value at m equals 6. X out value is going from -1 to 4, but really, who knows what the other y values exactly are? And yet, with this crummy picture, I claim you can determine that one of these statements is true. Okay. So let's try popper question 4. The definite integral from -100 to 200 of the function 5 dx equals which of the following options? Is it A, 1000? Is it B, 1500? Is it C, -1500? Is it D, 0? Okay, and then we'll just round this off with one last popper question 5. We'll say the answer is E because we never put E. All right, guys, thanks for letting me explain this so long. I hope it's making enough sense. I'll talk to you later.